Okay, one of the last steps in data understanding is to investigate the relationship between variables, especially in our case regarding the potential features of our data set and our candidates for label values. This is something that can be easily done when we just have a few features, but it's possible that some of our data sets may have hundreds or even thousands of features. But let's walk through the process and we'll see how it's done, and we can work with that. So the first thing we'll do is consider our bivariate relationships. Again, we're dealing with the insurance data here, so we've got these data fields. When we analyze each data field individually, we can see that we can evaluate our numeric data set using scatter plots to look at the distribution of data. We can use a Pearson correlation to work with that. So when we have numeric versus numeric for our label and feature, then we use a scatter plot. When we've got a numeric label and a categorical feature that we're evaluating, we're going to perform an ANOVA, one-way ANOVA, and we'll probably investigate the data visually using a bar chart like we see in this table here at the bottom of the page. And then when it's categorical to categorical, we use a chi-square measure and visualize it using a crosstab heat map type approach. So we'll take a look at these approaches, and we'll start off with numeric to numeric. Those are the ones that most of us are probably most familiar looking at from our stats class. And as a matter of fact, if you have a pretty good background in stats, you may know all of what we're about to talk to in the next few sections. You can kind of skim over these and just make sure that you understand what it is that we're doing in these sections. But of course, if all of that's still a bit hazy or it was a while back and you can't quite recall, well, you may want to review the topics in a bit more detail. So for numeric to numeric analysis, we're going to come up with some kind of predictive equation. All right. So you can see, for example, in these three diagrams at the bottom of the page, we've got a series of data points that are all in perfect lines. So this would be our ideal situation where every data value can be perfectly predicted. And as you can see there, our R, or our R squared for that matter, is 1. Although when we have a negative direction, our R itself is negative slope, so -1, but the R squared then again becomes 1 still. So you can see our R squared, you can see the equation for each of these slopes, and you can see that they're each made up of a series of data points, but they're so close together, it looks a bit like a line. Now, we hardly ever come across data that looks exactly like this. What we generally see is something a bit more like these, okay? So we've got data points that are scattered around, but there's an obvious pattern to that data. And here you can see we have pretty strong R's, R of 0.91. So that's still going to be a pretty high R squared, somewhere in the 0.8182 range. Same thing with the R for the chart on the right. We've got -0.87. We'll square that and come up with 0.657, somewhere in there. Now, just as a reminder, when we're looking at a linear regression type equation like this, the R squared is an indicator. The R squared was right there, 0.83, 0.75. The R squared indicates the percentage of variation explained by our model in the data points from the x-axis to the y-axis. For every movement in the x-axis plus the y-intercept, we can explain about 75% of that variation in the model on the right with our equation. So the higher the R squared, the more confident we are in that model, all the way up to an R squared of 1, which would be 100% accuracy. Now let's take a look at a couple more scatter plots, and you can see here at first glance we may not even notice, just eyeballing these without the regression lines, that there actually is a relationship. But if we see the line, look at the equation, we can see that there's still a reasonably high R, 0.42, negative 0.2 on the right. And both of those would be considered a reasonably moderate effect. So why in the world would we even visualize if we can just go ahead and get our equation, our linear regression equation? Well, it's a good starting point for us to see what the data distribution looks like and whether that trend in the data actually resembles a straight line or maybe something else. So here's something, linear regression can be used even with nonlinear data. We just have to determine what the nature of that nonlinearity is, and then we can make some adjustments. As we look at R square or R values from a statistical standpoint, we've developed a kind of a common guideline for determining what is a meaningful R. And we call this Cohen Standard. And you can see if the R is somewhere between 0.1, 0.29, then we'll say, well, we've got a pretty small effect here. If we've got from 0.3 up to 0.49, then it's a medium effect, but anything 0.5 or above, we would consider a large effect. That could be negative. So basically the absolute value of R being 0.1, 0.3 to 0.49 or 0.5 or above. We can also determine how confident we are that our estimate is reasonable by developing the p-value. And this is something that you'll see as we start working our way through some of the modeling techniques we'll use going forward. The linear regression, so the linear regression equation ends up basically plotting the line on our XY coordinates that we think best represents the pattern of our data. So before we start building our scatters, let's start filling in the data exploration section of our CRISP-DM documentation. So for each variable pair that we're going to analyze, we want to include the following. First, what are our expectations for how this relationship will work? And here's where you can apply any domain knowledge you may have in the problem set area, any experience you bring to bear, just having worked with that type of data or that type of situation before. You could also do your research, do a little Google Scholar search to see what the literature happens to say about those types of variables and their relationship. Next, we can insert our scatter diagram. We can figure out what the equation for the trend line we've selected is, what the R squared value is. And as we'll see when we start walking through this, we want to take a look at different trend lines. They aren't all just pure linear, and see which one is the best fit for that particular data combination. And then we want to document and explain what it is we found, including any inclination for moving forward with the predictor variable that we're working with. We can also write up anything additional that we see about the data that wasn't necessarily captured in the statistical tests that we've run. So let's go through an example. We can start building a scatter diagram between our variables. If I go to Power BI and I create a new page, let's insert a scatter and evaluate age and charges. So here we can see, and again, before we look at the scatter, we'll want to disaggregate. So we will say don't summarize for both age and for charges. And when we do that, we get an interesting scatter. We can look at it and see there are 3 distinct bands of data points. Each of them has more or less a similar looking trend, but at various bands in the charges. So we don't know why this is yet, but that's something to keep in the back of our mind. Now, so the first thing I can do is I can go to the Analytics tab of my visualizations pane and insert a trend line. And I'll go ahead and add one now. And you can see we get a trend line that's just a little bit above that bottom band, but it's below the middle and the top tier band. Well, it looks like it's pretty low. Why do you think that is when we have so many data points above? Well, you can see that first band is really tightly packed, so there are a lot of data points in there. So if you think of each data point as having its own gravity, we basically have more of a gravitational pull down towards those lower data points versus those upper ones. Now, when it comes to Power BI, our trend analysis is limited to this straight line view here. So what I typically would recommend is let's go into Excel, where we've already calculated some descriptive statistics, descriptive univariate statistics, and let's do the same scatter plot for age and charges. So I'll insert scatter chart, and that goes right here. And I'll make it just a little bit bigger so that we can see. Yeah, we still have the same data distribution here. First thing I'll do is I'll change the title of the chart so that I know this is age charges by age. How about that? Okay. So age is on my x-axis, charges on my y-axis. Now tell it I'd like to see a trend line. So I add the trend line, and you can see we get the trend line pretty much in the same spot we had in Power BI, sort of a little bit above that first big cluster, but below the next 2 clusters. I can now, with my trend line selected, go over here to my Format Trend Line, click over here on the different options. First thing I want to do is show the equation for this trend line, and then also display the R squared. Now it shows up right down here, right by the trend line, but it's covered up and mixed in with all of my data points. So I'm going to drag that up here into a blank area of my visual. And I'm also going to go here and make the font a little bit bigger so I can see it as I work with different options. So right now I can see I have an R squared of 0.0894, and I've got a regression equation with an intercept of 3165.90 and a slope of 257.72x. Okay. So let's go back. I'm going to click on the trend line again. And you can see by default, the trend line comes up linear, but I also have some other options that I can see. So let's test out logarithmic. So in this case, I'm going to take the natural log of my x value in this case, and you can see what happens is the equation changes. I now have a different y-intercept, negative 19,067, and a different coefficient for my x. I've got, first of all, I've converted x into the natural log of x, and then multiply that by 89.5. So 8,989.5 times natural log of x minus 19,067. I get an r squared of 0.0841. Now, what did I have before? I had 0.0894. So logarithmic, not as good as linear. What about exponential? My value here, and you can see it goes up to 0.901. So 0.894, 0.901. And the equation now is y equals 2,308.3 times e to the power of 0.0345x. So this is basically the opposite of taking the natural log, and now we're taking e to whatever power times x that we need. All right. Now, the other option we have down here is a polynomial equation. And you may remember those. And in this case, I'm going to use x and x squared. So I now have another factor in my equation. I've got an intercept, 6508.6 plus 64.573 times x itself, plus 2.4389 times x squared. Now, this is a polynomial. When I go up to an order of 2, I can actually increase this again and now include a cube of x. And that takes my r squared up to 0.091. I can go even more, 0.0913, take it up to the 5th power, 0.0925, and up to the 6th power. And again, I have 0.0925. But as you can see, as I increase the number of exponents that I'm evaluating, the equation becomes more and more complicated. And I also am going to have to create new calculated variables for each one of these. So the rule of parsimony fits here, where we want to, and you can also see the line starts to change a little bit as well. So when we have diminishing returns, and this is something that we don't really necessarily have a hard and fast rule for, but you'll just kind of get a feel for it. I'm not getting a whole lot more r squared for making this more complex beyond a certain point. So the question is, do we want to stick with that and find a stopping point? Let's go ahead and take one last example. That's the power example. So this would be, I can take 96.333 times x raised to the power of, and in this case, it's not an even exponent, it's raised to the power of 1.2595. Again, here with an r squared of 0.901. All right, so let's just take a spin through these again. 0.901 with power. I start off with 0.0906, polynomial with an order of 2. 0.0841 logarithmic. 0.0894 linear. And 0.0901 exponential. So exponential, polynomial, power. It looks like polynomial is probably the best way to go. Now we just have to determine where to stop. So I have an r squared of 0.0906. If I increase it to the order of 3, now I have 0.091 even. So I've increased it by 0.0004. If I go to the 4th power, 0.0913. So that's not a lot of incremental gain for another power. Now I do get a bit more all of a sudden when I go up to the 5th power, 5th order, power of 5. And then it stays the same when I get to the power of 6. So just for simplicity's sake, I would probably stop right here at cubed. And now I have my equation, my regression equation. My r squared, and what the data looks like. So now let's go back to our text where we've created our data exploration, we'll start with charges by age. So we can start here by saying, well, we expect charges to increase, or we can be more formal with our statistical language. We could say we can expect charges to be positively correlated with age, because as people get older, they are likely to require more medical care, which will result in more charges being passed through to the insurance company. All right. And then we could take our scatter plot and drop it in here. And I'll just go ahead and do a quick copy. Paste. And you can see the regression equation and the R squared both come in. But we'll want to go ahead and document this officially as well. So we could say R squared equals 0.091. Charges equals 600.9 plus 586.89x plus, or actually age, plus 11, or minus 11.561 age squared. And we'll have to make that a superscript. Plus 0.1161 age cubed. We could also insert a full correlation matrix right in this area as well, maybe up at the top, so we can get our initial introduction to all of the fields and the potential field combinations that we have for the variables. But now that we have our scatter in here, along with our equation, our R squared, let's go ahead and set that up properly. We can now note charges do appear to have a positive relationship with age. The effect is moderate with an R value of, and here we could calculate the square root of 0.90091, which is going to be about 0.3. As a matter of fact, I can bring up calculator. 0.091. Square root of that is 0.3016. So we'll round that up to 0.302. Now, here's where we have an opportunity to note that we have three distinct bands of data. All right, so although our statistical analysis does not show this, our data also has three distinct bands of data points in the distribution. And the meaning of these bands may merit further investigation. So to recap, we have determined that our polynomial equation that uses both squared value of age and cubed value of age is the one that we're going to move forward with. Now, just a reminder, we had others that included age to the fourth and so on that actually provided a slightly higher R squared. So that's something to consider, but for this example, we'll just stick with age cubed. So what we can do in Power BI is now we're going to create a new column. And we'll call this new column age to the power of 2, I guess. The formula for that column will just be age to the power of 2. And we get our new data field. And we can add another data field as long as, or another column as long as we're here. So let's create another new column and we'll call it age cubed. And we can go to our data view and just double check to make sure everything looks right. So age 33, we've got our bins that we've got our ages in. Age cubed or age squared is 1089. Age cubed is 35,937. So it looks like our calculations are working well. We can now use those two in our visualizations if we want. And at that point, we can move on to our next visualization. And that would be the next pair of data points that we want to evaluate. So you'll note we've got charges, which is our candidate, our likely candidate for a target variable. We've just done age. So we'll also want to do children versus charges, and then also BMI versus charges. Remember, when you do that, you want to evaluate each potential trend line to see which one works best. And then for polynomial, you can check different orders of polynomials to see which trend line is going to work best for you and then proceed accordingly. Go back to your write-up, update what you have, and that will allow you to move forward once we get into modeling. All right, so we'll wrap things up for now with that, and we'll move on to documenting what you want to do when you have your categorical variables that you want to evaluate against your target variable.